Doc, the physics of sound and music. We have a request to review circuits, and let's do circuits part 1 here, chapter M, and call up the PDF file, and let's see what we can do here with this chapter. Well, let's go down to the first circuit, since this chapter is basically 4 circuits, and the first circuit is a simple battery arrangement with the bulb. So here's the symbol for a battery, a plus and a minus with a long line and a short one. This would be one cell, 1.5 volts. I have 3 of them here. That'd be 4.5 volts, but engineers are not that picky about how many of these you show because they often write the number to the side. So you would see 4.5 volts written to the left here. You can think of this as a pump that pumps the plus around the circuit. Plus actually wants to go to the minus because of the electrical force law. Opposites attract. However, some folks think of this as a water pump where you pump water around in a circle like this, and then when the water goes through this element, it does something, like it's going to glow. Using the electrical analysis, since plus and minus are attracted to each other and the battery separates them, then the plus wants to run through here the bulb. When it goes through the tungsten filament, it glows. The tungsten glows, rather. Chemical engineers and chemists would take issue with me because they say that really the electrons move in the wire, not the plus. The minus moves. So the electrons would move this way and come to the other end. The battery would separate the electrons, and then they would go around again until the battery should become dead. Then it would stop doing it. But electrical engineers just think in terms of plus moving and don't worry about the chemical details. So we come here to the next example, which is a circuit that's not as say interesting at first glance, but really it is, because that's a toaster. A toaster simply has a resistor, and well, they're not just a small battery, but it would be 120 volts when you plug into the wall, and that's an alternating current. So here in this simple circuit we have one battery cell, and the current's going through the resistor, and you could demonstrate here, see Ohm's law. Ohm's law is equal to the equation where you have what V is IR. So here if V is 1.5 volts and the resistor here has a resistance of 15 ohms, then you have the R, you have the V, so the I is V divided by R. 1.5 divided by 15 is 1/10, so that's 1/10 of an amp. So we move here to this circuit, the dimmer circuit, where if you put a resistor in the pathway, the bulb will not glow as bright. Here is the flash circuit, which introduces another electrical circuit element, the capacitor, which can be thought of as 2 plates. When you attach this wire to the left, then you charge up the capacitor, where you think of the plus flowing this way, plus over here, and the absence here would be negative, and they can't get together. They can't complete the circuit because there's a gap in there, so they just charge up. And then here, if you throw the switch to the right, then the plus can go through the bulb to the other side, cancel out, and the bulb will glow during that short period. And since this is not a battery, when the plus gets down to the bottom, you have neutrality. The circuit is over. There's nothing more that's going to go on. The delayed light is really a delayed light when you turn it off. It takes a while to go off, and that introduces another element, the transistor. The transistor is such that if you have a little bit of current going in the back door, you get lots of current from top to bottom. If there's no current going in the back door, then this is shut down, doesn't work. So here we have no current going in the back door because there's a gap here in the circuit. This circuit's not complete, and therefore nothing happens. But when you squeeze this, and this touch switch makes this connection, then the plus can run over to here, charges up the capacitor, and get through the resistor here to then activate the transistor, which then allows lots of current to flow from top to bottom due to this battery here. Notice the resistor will make it so that only a little bit of current goes through the transistor. The beauty of this circuit is that when the little child here releases the switch and doesn't squeeze it anymore, then the charge on this capacitor will drain through this resistor to come back to the ground here. So the bulb will stay on for a little bit, and then after about 30 seconds or so, when all the charge has been released, then you have no more current going through the back door, and the bulb circuit shuts down, and Mama is happy because Mama doesn't have to go out and buy new batteries, which would be the case if the kid simply had the battery, this light bulb on, flashlight on, and left it on the sofa while he or she took a nap. Then the batteries would run dead. So let's look at what else do we have here. Oh, this is a nice review. So this would be here 4 circuits. Notice that here we have a battery and one circuit element, the bulb. Here we introduce another circuit element, the resistor R. And here we introduce another circuit element, the capacitor. And here we introduce still another one, the transistor. Now it's this last one that uses all the elements once and only once. The battery, the bulb, the resistor, the transistor, and the capacitor. And this is one of my favorite circuits because it uses once and only once these circuit elements and shows you how they work together. So that's the review of the circuits, and here's the definition of power, that if you have anything here and a current is going through there and there's some voltage across there, then P is IV or P is VI. Notice that you can also use this to define your voltage in terms of your resistance. There's some resistance here, then V is IR. A nice little review of the two formulas. And here we see an application with alternating current where the current's swishing back and forth, 24 amps, and this doesn't care. This gets heated up anyway, a dryer element. And here, if you want your power, you have to multiply the two numbers. Now, these numbers are a little bit weird because I'm using real numbers from home, and your house has a 240 volt extra special plug for your dryer, and that draws something like 24 amps. And then if you multiply those two together, you get 5,760 watts. That's a lot of wattage, and that's why it's expensive, say, if you're drying clothes all day. So here we have power, and let's see what else. Oh, well, that's just a little chart that shows you how much wattage you have for various appliances. Notice that you get wasted when you use the electric range and the stove. Say that's very expensive, that heat that comes from there. While nightlight, 4 watts, very, very, very cheap to run. And a lot of your electrical equipment here for audio and iPods and radios and things like that. You can even use batteries that you charge up. And the last part, well, we don't really need this. This is just for your interest if you want to know how you get wasted. And we mentioned in class that we get wasted more if the current is like some intermediate value. See, if your heart freezes, that's actually a better chance if the rescue team is nearby to get you back compared to some kind of ventricular, say, fibrillation where your heart is undergoing some kind of anomalous beating. But that's extra. You don't need to worry about that. So that takes care of the circuits.